the issue come up of the keep saying that the lens thing's not all the way open. So I just like stuck my fingernail in there a little bit. Taking all my scenes. Not the camera. I think I'm streaming right now.
I don't know that is the links in an email.
If you search for media area official on YouTube.
So, just I don't really know. I should move around the camera with the speaker, or what do you want me to do with the camera?
Oh yeah, I'm just hearing what us talking about.
Oh, yeah. Well, because this mic's on right now.
Yeah, yeah.
Hello.
How are we doing this?
Sorry, that was like a test hello, not like a. Hi, everyone.
Pretty good.
Yeah, I think we.
Hi, good morning, good morning, everybody. Welcome to Workshop Day. I'm not going to do an official No Time to Wait welcome because Workshop Day is a more non-official, on-conference style program for the next couple of days, but I'm so happy that you all made it. What we'll do today, we have 3 workshops. How many workshops, Dave? 3 workshops, great. And they're all very popular and they filled up. So if any of you cannot make it or doesn't want to do the workshop anymore, please let us know because there are waiting lists. There are people that are hoping to get into those workshops. What we'll do now is we'll have quick presentations of what you can expect during your workshop. It's maybe a bit of a improvisation. So there's Joanna. Can I put you on the spot right now and just walk us through your workshop, maybe, real quick? So that we can tell people what to expect. Thank you.
Hi, it's nice to be here with you all. So my presentation's more of a presentation than a workshop, I'm afraid. It's going to be just talking to you about the open source scripts that we use at the BFI and the way that we use FFV1 at the BFI as well. So it's really workflows that are built on the tools made by this community and my constant gratitude to you all for continually building and supporting these amazing tools. So.
Yes, thank you, Joanna. So for those who are interested to do Joanna's workshop, she'll be outside and you can just group around her. And then we'll get you to your room. Where's Jerome? Is he here? No, okay, so I'll ask Dave to present his workshop.
Well, I can talk about Jerome's workshop. I believe it's a small workshop about raw cooked, which is a tool to convert the kind of output that comes from a film scanner into a losslessly compressed file. So the primary use case is it takes this big mountain of DPX files where you have like one image per film frame out of a film scanner, and then it, which could potentially be tens of thousands or hundreds of thousands of single files for a film scan. So what RawCook does is it takes that like uncompressed data and makes like one Matroska FFV1 file out of it. So I think like I did a 4K scan recently and it was about 1.5 terabytes, I think, per film reel. Whereas like a RawCooked file would be about 1/3 the size as a lossless format. Jerome's workshop is in a room that's a bit smaller than this one. I think it has a capacity of 8 to 10. So could I see like a raise of hands of who's interested in heading to that workshop? Okay, that roughly fits the number. I'm going to jump over to the workshop room and just make sure there's not like 8 people in there like starting already. But yeah, that's, so in a minute, like we'll walk over to that room. And then is Adela still here?
No, that's why I didn't. I'll get it, but your workshop.
Oh, okay. I will present about my workshop. So at 2 p.m. back here, I'm going to give a workshop about live streaming, just sort of this setup, and we'll go through some exercises where we break off into small groups and do little live streaming samples. We've been live streaming at No Time to Wait since the first one in 2016, and back then it was just like a camera connected to a computer streaming out, and now we connect in the slides. We have much better audio. The first time we just had audio coming off the camera, and it was a bit difficult to watch or follow. but I think every year our live streaming gets a little bit better. And we usually just make a list of like what equipment we need and gather volunteers to bring it. So that'll be at 2 o'clock. For today, lunch and all meals are on your own, but there'll be some food here on the everydays, and we'll have a dinner Thursday night. We have a coffee now.
Yes, so today it's self-catering, but there's some water, free water on the bar, and then the coffee is open. I don't know if you said that or not.
No, I don't drink coffee. So.
Yeah, so the cafe here is open. Tomorrow you'll have all the refreshments you need. I couldn't find Adela, so I mean, because we would like to say thank you to our host, the National Film Archive, for having us and for being so generous with their time and resources. But I couldn't find our host, so I don't know. But thank you. Yeah, we can still.
And then, do you know how to get to Jerome's workshop from here? I realize I don't.
That's probably where they are.
Okay.
I don't. But we'll figure it out. We'll figure it out. Then, just so you know, tonight there's a screening. If you haven't signed up for the screening yet, let me know. Tomorrow is the dinner. We're at capacity for the dinner, but so if you can't make the dinner, please let us know so we can bring people in that are on a waiting list. But these are all information we'll repeat tomorrow. Yeah, I'll just get into, I guess, your groups until we figure out where the other room is.
All right, well, yeah, we'll
Thank
give you
you.
a few minutes to chill, and then at 11 o'clock in 10 minutes, we'll start Joanna's presentation here and Jerome's presentation in the other room. So I'm going to check on the other workshop room, and then I'll gather folks going to Jerome's workshop a few minutes before 11 so we can get over there. Thanks. Yeah. One got canceled. No. There's, oh yeah. Sorry, there's another workshop. Jerome's also has a 2 p.m. workshop about media conch and media info. That's another limited capacity one that'll hold like 8 to 10. There was another workshop that was like a hackathon workshop that was going to happen at 2, but that one unfortunately is canceled. The speaker couldn't make it. Yeah. Set up Joanna. All right, everybody, Jerome Martinez is here. So if you're heading to Jerome's Raw Cooked workshop, you can gather out here in the hallway. We found out the room can hold a little bit more than we expected, but if there's more than 14 of you, we need to kick some of you out and make you go to Joanna's workshop instead. Yeah. Oh, I would love it if you would make an announcement. Yeah.
Has this been, has the link been shared?
What was in the last email? It's bit.ly/nttws notes.
Oh, nice memory.
Well, I don't know. They're all. It's like the same link every single year. We just changed the number.
Shall I say something?
Would you love to? Yeah.
Yeah?
Everybody, we're gonna have a little mini announcement about the collaborative notes that we have.
Hello, my name is Randy Cicchini. There's a collaborative notes document going, so if everybody can contribute to that, it would be a wonderful way to make a shared memory, and you're going to share the link.
Oh, yeah, I'm just gonna read a URL or say a URL. It's just bit.ly, bit.ly/nttw7 notes.
And is it in
Which is-
email?
Yeah, the last email I sent out, if you go to the bottom, like all the good links are there. So it has like our notes, our attendee list. Alessandra, you have something? Oh, we can tweet it too, sure. Okay. You could say, of course.
Is the link there for the WhatsApp?
I wish I had all links on the.
I don't know, understand. So that's why I don't know.
It's just like bit.ly, no time to wait 7 WhatsApp.
Yeah, we'll just tweet out the WhatsApp group.
No, we shouldn't do
No,
that.
we shouldn't do that. Okay, I think everybody who wants to join Jerome's workshop can gather in the hall, and then Adela and Jerome will take you to the room. And for those who want to stay for Joanna's workshop, can just stay in the room. Thank you. And yeah, you can, voila. Thank you.
Hi, we're going to get started if that's okay. My name is Joanna White. I'm a Knowledge and Collections Developer at the British Film Institute's National Archive. And in that position, I work with the workflows. So I build open source workflows and sometimes closed source workflows for all of the video asset management and various other document management and interactions that communicate between our CMS system and our Black Pearl long-term storage system and various other things. But I'm going to be talking to you today about two things. So one is how we use FFV1 at the BFI, and that's the first presentation. And the second is some work that we did about 2 years ago to replace the media asset management system that we had in BFI called Ingestion, which was operating a bit too slowly for our workflows as our workflows increased. So we're going to be looking at the scripts that we've put in place to replace that media asset management system. So we'll start with FFV1. I've called this presentation How We FFV1 because at No Time to Wait 3, I was thrown into my first ever roundtable for No Time to Wait that was called How We FFV1. It was chaired by Sophie Bunce and had Dave and Carl-Jürgen Hoyas there, and I was completely unaware of the company I was keeping in that presentation. If I'd known, I would have been far more stressed than I was. So I was newly into FFmpeg, and I was invited to take part because I'd just been doing some very casual experimentation with FFmpeg at that point as a regional archive that belonged to the BFI's bigger network of archives. It was a pivotal point for me because the information and the community support that I got from that point led me to end up with a role in the BFI working with raw cooked and FFV1, and then eventually into the developer role that I sit in now. And I'm very grateful, really, for the support I've had from this community to get me to that point. So this presentation today is not, it's going to look at how we work with FFV1 codec for our videotape workflows. I'm only just going to show you the raw cook repository that we have. I've done a lot of presentations for raw cook before, so I didn't want to do that today because also Jerome's doing a similar presentation in the other room, so we won't be touching on raw cooked, really. So we're going to cover intro to FFV1, just a very basic overview because I'm aware not everybody may know what the FFV1 video codec standard is. Then we're going to look at how we convert our V210 MOVs to FFV1, then how we convert our FFV1 Matroskas back to V210, and then something that we uncovered in that process, some problems we were having with lossy buffers around the outside, which Dave very kindly helped us to remedy, but I think it's useful to share with you exactly what that problem is because I expect more people, as they work more with FFV1, may encounter it and will want a solution for it. Then we're going to look at our FFV1 to ProRes and FFV1 to H.264 FFmpeg commands very briefly, just to give you an idea of what commands we use and the flags and how they work. And then some capture card technology information. So I'd like to quickly introduce FFV1, as I said, for anyone who isn't aware. The FFV1 codec is a lossless video codec developed initially by the FFmpeg community and is now standardized under the Internet Engineering Task Force. This is the data tracker for the standardization work shown here. So FFV1 first launched in 2003 and was standardized in 2021. So we'll just have a look at that timeline. Thank you to Dave, who's got a video with this timeline in. I've just slightly reworked it for my own use today, but basically this is Dave's information, so if anything's wrong, it's not my fault. So, in 2003, FFV1 was launched, which means this year it's 20 years old, which I think is quite an achievement. Yeah, it is worth applause. In 2006, the first version was frozen. I should say it was launched by FFmpeg, and I think essentially Michael Niedermayer, I'm not sure, developed the project. So in 2006, that first version was frozen. In 2009, the codec was picked up for preservation use. I'm not sure by whom, but I'm guessing people in this room. 2010, funding improvements were found because I think it was recognized that it was going to be useful for the preservation communities. In 2012, 14-bit RGB was added, along with multi-threading and slice CRCs. So multi-threading of FFV1 in an FFmpeg, as I understand it, makes encoding times much faster. And slice CRCs are multiple checksums that are present in each frame of the FFV1 file. So this means that if a file suffers any damage over time, bit flip or sector loss, etc., then FFmpeg can isolate exactly where in that frame, within, say, maybe 16 or 24 points within each frame, where that damage is. And as I understand it as well, the slice CRCs are how FFmpeg multi-threads. It takes each slice from within that and spreads it across all the threads of your CPU, and that's how the multi-threading works. So in 2013, the official release of FFV1 version 1.3 was released. In 2014, the pre-former project started. Pre meaning preservation and former meaning formats. So this European Commission funded project supplied essential funds for the development tools and standards that allow archivists to have better control over their selected open formats. And for this, they selected FFV1 and also the Matroska wrapper. In 2016, the pre-former project saw beginning of work towards the standardization of FFV1, and also I think it added in 16-bit RGB. And in 2021, the standardization was ratified, as we saw through that IETF document. Okay, so there was a question I asked at No Time to Wait 3 for the how we FFV1, and that is how can I see when there's a problem, say if there's bit flip or damage in the FFV1 file. I was really curious at the time to work out how I could work out where the damage was, what it looked like, and I wasn't really sure how that slice CRC feature was useful to me. So this is a hex editor. Kieran O'Leary showed me how to use one. Please don't use it on your preservation files, but basically it lets you go into a file at the binary level and hack it and break it. And this is me doing that, typing I love FFmpeg into the binary of an FFV1 file so that it simulates bit flip or damage to a file over time. So when you then come back out and you run it through FFmpeg, what you get is these slice CRC mismatch warnings. And that has the timecode at the end as well, exactly where in the frame it sits, where in the stream it sits, sorry. And I just think this is a wonderful tool for being able to find out over a period of long-term preservation whenever you put your FFV1 back into some kind of FFmpeg environment, it's going to tell you exactly where there's damage, if there's damage. If you've got 2 copies in long-term preservation, that means you can potentially check the other copy, make sure there's no problems with that tiny little piece of video, and you can edit and sub and make new masters from it, that kind of thing. So I just wanted to share with you how you can use those slice CRCs. So our FFV1 code base is open source and available to view in our GitHub. And we've got the name BFI Data DigiPress. The repository is called the Transcoding scripts. They've been there for a little while, but I've recently added a few extra scripts in that haven't been there. So the repository features descriptions about how our code operates. The repositories are not packaged necessarily for easy installation, but they're useful, I think, for institutions who might want to know more about how we do our coding and work, etc. It can be downloaded via git clone quite easily, but the code isn't agnostic particularly. It's very much written to work with on our own workflows, so there's lots of particular kind of environmental paths that you would need changing and updating. But again, as I say, I put lots of notes in all the code, so hopefully if you're learning to code with Bash or with Python, then there's some things that will be useful for you in these repositories. So you can navigate through all of our transcoding code work, including viewing our media conch policies, which I'm gradually adding one by one. And yeah, it wouldn't be hard to borrow sort of functions from our Python code and try them and play with them in your own workflows. Please not in a safe environment, though, not with your preservation workflows, definitely. So the first script is our v210 to FFV1 Matroska script. So for a little context, this script has been working on our Heritage 2022 videotape digitization project, which requires the BFI National Archive to collect and transcode 100,000 different video projects. External suppliers to the BFI digitize those tapes for us, and the BFI digitize them ourselves for regional and national archives in the UK. We received the V210 MOV files from different suppliers for conversion to FFE1 Matroska format, which was then put into our long-term preservation. Before we did that transcoding work, we needed to pass all the V210s through a media conch policy to ensure that there would be no breaks in our transcoding workflows. And I just pushed a button to make that thing go around. That's embarrassing. The shell script completes the transcode with frame MD5 comparisons at the end as well. So we'll have a look at the shell script now. Actually, we'll look at it after this. Before we start transcoding, I mentioned that we put the FFE1 Matroskas, before we start transcoding to FFE1 Matroska, we put the V210s through a media conch policy. So this is the first half of that policy. If you're not familiar with media conch policies, then it's open source software provided by Media Area, which is Jerome Martinez. If you've just used media conch via a graphical user interface or through their software, then you may not have seen an XML policy in this format before. It's this policy that our scripts use via the command line to carry out batch assessments of files. If it passes every single thing in that policy list, then we get a pass statement returned back to the scripts, and we know that the file can be moved into the transcoding workflow. This policy is basically an AND policy, which means everything listed in the rules needs to be matched in the metadata of the file. The policy includes name fields where you place the description for the use on the left, a value, which is the metadata item that it needs to match to, the track type, which is usually video, audio, or general, an occurrence and an operator. So here there are checks for exact matches on frame rates, color information, video pixel height, and interlacement. The inset rules towards the bottom are generally nested OR policies. So that means that only one of the items within that OR policy needs to match to get a positive return back for us. So that's such as bit depth or video pixel aspect ratios, where we accept a number of different options. And in the second half, which is just as long, we have more OR policies, checking the video display aspect ratio, format, audio codec, video width, etc. The very bottom rule, if you can read it okay, is a separate AND policy, which was a later addition into our workflow. It checks for source delay timings in the audio tracks. So we were having source delays between the audio and the video, which were breaking our transcodes. So we needed a deep check to ensure that there was no source delay in the audio tracks in our files that we received. So just looking at that one in particular that I've highlighted, you can see towards the end it says scope MMT, which flags to media conch software that the rule is to be applied to the media trace block of the FFE1 files. I thought it might be helpful just to talk you through how you might use a media trace rule like this quickly, because I know when I was trying to work it out myself, it was a little bit hard to get my head around. So both media conch and media info can generate a deeply detailed report called a media trace report, which you'll see here. This is a technical report that demonstrates the binary architecture of an audiovisual file set out in blocks, and the report showing here is just such a media trace report. So many audiovisual file formats are based on chunk-based storage of metadata, where a block of data will either contain a data payload or other blocks. With QuickTime, these blocks are called atoms. In AVI, they're called elements. Chunks, sorry, and in Matroskas, they're called elements. So whether the source format specification calls it an element, an atom, or a chunk, or another term, media trace will convert it into a block of data, as shown here. And within those blocks are data fields. So the media conch rule we just looked at was built from blocks of an SD video file, and it needed to check that there was no source delay in the audio track. So the rules value field is built from the names of the blocks starting at the top with file header. Then the next inset block is, it takes the track, and then the next inset, it takes the track header, and then in the track header block, it's looking for the track width. And in this field particularly, it's looking for that 0.000 match. And the scope MMT tells MediaConch that it needs to look in the media trace in this way. So you may wonder why I needed to find the width indication of an audio track. It was because if I needed to identify that it wasn't a video track, and by picking the width to 0, then I knew that the source delay that immediately followed it would be an audio track and not a video track. So I'd often seen MediaConch policies using this scope MMT and wondered what it represented, and I have to thank Jerome for his help in telling me how to use the media trace in this way, and I just wanted to share it because I think it's a really useful tool. It's like a superpower when you're trying to inquire for really deep metadata in a video file. And you can find out about media trace more on the media area website. So this is the bash script. We've sorted our v210 mobs into the pass and fails now, and we've just got the passes that are coming through into this workflow. They're moved into a transcode watch folder, and from here a shell script finds them and converts them into FFV1 Matroskas. This script was written by my predecessor, Edward Anderson, and was later enhanced by Head of Data and Digital Preservation, Stephen McConaughey. It receives one file path at a time and just processes that one file before exiting and being relaunched again for another file. So I thought we'd just go through some of the steps in the code, if that's useful, and just talk about the code. So you'll see in this block global variables for paths that are $1 and $2. And these are arguments that have been supplied into the script at launch. So the 1 is the path to the v210 mov, and the 2 is a bash watch me do method, which Edward built into the script. And it looks for the statement created, which means that the file can be processed. Functions for log creation and checking downtime control restrictions are next. At the BFI, we have a downtime control JSON file, which we use by changing a bool from true to false when we want to stop certain script actions across all of our servers. So it's quite a useful little way just to, whenever we come to patching servers once a month, for example, just to change all of the trues to false to make sure that all the scripts stop. Saves us having to go around all the different scripts and stop them all manually. Okay. So the script begins at this point, and if the conditional statement, checking that the number 2 is equal to created, and then it logs the example with just the word log because we've built that log function earlier on. The control check would exit here at this point if it found that transcode H22 key in the download control JSON was set to false. So it checks for the correct MIME type, video, audio, or application. If it matches, then it proceeds. And the MIME type is the multipurpose internet mail extension. It's a standard that indicates the format of a file. We tend to divide our files into 4 categories. So that's video, audio, image, or application. Application covers any type of binary data that doesn't fall explicitly into one of the previous 3 types. Sometimes I do find MXF files fall into that application, and MPEG-TS files actually from our video off-air TV recording, so it's not always foolproof. So the next is to check if FFprobe returns a 0x code against the video file. So that means that the file is basically a well-formed video file, audio-visual file. If it doesn't, the script will exit at that point. At this point, we configure local variables for our frame MD5 paths and temporary and permanent file names. It uses Linux's base name feature to capture the last name of the file path, and from that build the file name variable. It checks if the temporary file name already exists so that it won't recreate a file that's already being processed. And it also checks if the finished destination exists, so for the same reasons it won't create a file that's already just been created by another script. It also checks for v210 mov frame MD5s if they exist already, and if they do, it deletes the existing frame MD5s and recreates a new one for the v210 mov. Is that where I'm at? I'm a little bit behind myself. So frame MD5 files like this one here are generally used to validate lossless transcoded files like FFV1 to V210. They're like a standard MD5 checksum, but a frame MD5 is a more granular version of a regular MD5, allowing frame-level checksum generation for every frame of an audio-visual file. The frame MD5 lists all of the frames and their individual hashes for 1 video stream and 2 audio streams, which is the default, but you can change that with your commands. So the audiovisual asset is decoded to raw video. You can see that in the codec ID at the top by the frame MD5 command, which is run out of, it's one of FFmpeg's tools, basically. It's worth noting, if you want to store frame MD5s for a little while, I thought it would be a great solution for the previous archive that I worked at, that they do change over time as the PIX format function changes in FFmpeg, so your different FFmpeg versions might create completely different frame MD5s of one particular video asset. They're both correct, it's just that the pixel format has altered the way it converts it to raw video, so you won't be able to store them for long-time preservation check. The hash code, I believe, is the bit that changes. Does it? That's great. The layout of the frame MD5 also changes too. Thank you, Peter. Okay, so the next stage of the script is a log note being written to the transcode, which is at the top. And then using media info, we extract the input standard, PAL, SDR other, and supplied video height. In this example, the media info command is being called within the parentheses allocated to the variables input standard and height. Variables are a name for a kind of container that holds bits of, or a type of data like integers, such as numbers, strings of texts, or float numbers, that's numbers with decimal places. The variable name is the way you reference the data retrieved from media info. So this section now checks if the file is PAL and if the height is equal to 608 pixels. Why 608 pixels, you might be wondering. Some of our 100,000 videotapes were from BFI collections and were captured in-house, and some of our video operations teams capture 608 line height for PAL source. And that's because we retain the 608 to keep the vertical blanking intervals at the top of the video in the hope of extracting teletext from the VBI in the future, still to be tested. So if it's PAL, then it encodes with the first block and color data specifying PAL SD, which is BT47TBG. And if it's not PAL, then the script just assumes it's NTSC file and encodes in the second block using the color data specified for NTSC SD, which is the SIMP T170. Otherwise, they're exactly the same. So next is a log note to state the end of the transcode that's output to the logs. This is a similar block here to the previous frame MD5 creation of the V210. So this is now making the frame MD5 for the FFV1. It checks first if it exists already, then deletes it and creates another one, because sometimes a lot of our scripts are going over the same files twice. So then using the Linux diff command, which checks for difference, the script checks the frame MD5 for the MOV is identical to the frame MD5 for the Matroska. So with the diff, it returns nothing if they match, but if they don't match, it returns the full list of the files that don't match. And this is what a mismatch might look like, using some software called Meld. This example shows the difference graphically with blue highlights for mismatched audio in this example, with arrows that attempt to show where the misalignment is. So this one, I think it's the audio files, which are the 1, and the video files, which show stream 0. This would be a very unsuccessful frame MD5 match that would return a fail using the diff command, and it would definitely be sent back to the vendors for recapture. If successful, the output is for the success, then the success variable is populated and a log's created that moves the command in. Sorry, that sentence makes no sense. It basically moves the V210 file into a success folder and moves the frame MD5s into a pass folder. And so that marks the end of the transcoding script and the log. The final act is to pass the remaining file list to parallel for batch renaming. So all of the prefixes, when we transcode, we prefix with partial at the beginning of the name so that no other scripts pick up that file. But at the point the transcode is completed, all those partials have the partial removed, and then the file is available for the next script to access. Oh, that's in that bit block there, my apologies. So to look more closely at our ffmpeg command, and this is really for anyone who's maybe not used ffmpeg before, we start with the ffmpeg-i and the input, which calls the ffmpeg program and supplies the input file path to it. This is command line kind of commands that you put into the, for using ffmpeg. We next use the ignore edit lists 1, which ignores the edit lists specifying MOV wrapper timecode mapping. We have the -sn and the nost-din, which is subtitle streams aren't being accepted from the v210 MOV. And we also stop ffmpeg from reading any standard inputs that might be made into it, which is the no standard inputs flag. We use codec for the video stream, selected as FFV1. We use the G1, which is group of pictures set to 1 frame, meaning that we want lossless interframe compression from FFV1 for this file. Level 3 selects FFV1 codec version 3. And then we select CA copy, which basically copies across the audio that we've got in the v210 MOV straight across to the FFV1 file. We use the very important map0, which maps all of the streams from the input to the finished file, except -dn means don't transfer any data streams, because I believe at that point that it was written, data streams weren't supported in FFV1 and probably still aren't, or not sure. Need to research that. So slice CRC1 ensures that the slice CRCs are enabled for the FFV1 codec. And slices 24 suggests that we want 24 slices per frame in our FFV1 files. Then we have 3 color pieces of information: color primaries, set for BT470, color trace, BT709, and color space, BT470. So this is PAL-SD coloring. Then we have color range 1, which specifies the full color range. It's passed from the MOV into the FFV1. -n answers no to any questions ffmpeg asks, and then it will exit if any questions receive the no. And then temp is the name of the output file for the new FFV1 Matroska. So this basic command has been responsible for the majority of the 100,000 programs transcoded to FFV1 Matroska since 2019. It's worked pretty hard, this script, but it's been very reliable. It's a pretty basic bash script, really, but you know it's done an awful lot of work. So it's important, one, as it saves us a lot of storage as well, because those 100,000 programs are now all roughly about half the size that they would have been if we kept them in v210 MOV. Okay. So why would we need to return the FFV1 Matroskas back to v210? There's 2 cases, really, in the BFI why we need to do this. Firstly, some of our regional archive partners in the Heritage 2022 videotape digitization project have archive policies that support long-term preservation of v210 MOV and ProRes MOVs in some cases. Secondly, our own archive staff sometimes need to complete complex edits on the videotape files that we have preserved, and the softwares out there at the moment that they use don't support FFV1 Matroska. So for these use cases, we've written Python scripts that have been developed to automate that move back to v210 file. And there are 2 scripts that we use. They're very similar, really, so I'm just going to show you the Heritage 2022 version of the script today. So this is the batch transcode H22 FFV1 v210 script. We use a shell script to launch it, and that's so that we can use some open source software called GNU Parallel to launch multiple versions of the script So we only have one Python script. It handles one input at a time, which is the file path for the file. But with the shell script kind of manages pushing all of those file paths into the Python script. So if you're playing with bash, it's worth noting that the shebang in line 1, which tells the computer what language it needs to read the script in, the -x in this case is there to print out verbatim message to you. It's like a test feature, which is really useful when you're starting to write shell scripts. It just echoes everything to you in the script, so you've got a really clear idea of what's happening. Global variables are established, including variations of transcode paths for selections of archive content. It refreshes the batch transcode text file, which is where it stores all of the different file names. It marks the start of the script run into the logs and confirms the paths that will be targeted in those logs. It finds, I haven't got any more. Let me move these down. That's it. It uses the find command to look in that supplied folder for any files that end with .mkv and haven't been modified in the last 30 minutes, which is important to state, because we need to make sure that files that are being copied into that folder, for example, aren't partially copied in before they're being processed and handed on to the next script. And so it updates the log finally before using the grep command to then grep that text file that it's written all the file paths into and supply them one at a time into GNU parallel. And as you can see, it says job 16 on there, so it will run 16 parallel Python scripts at once. So what's GNU parallel? It's really worth talking about. It's an open source tool made by the Free Software Foundation, and it's a really great way to start being efficient with your transcoding in a simple way without having to get into the complexities of Python multiprocessing, for example. It separates encoding jobs across your CPU cores, maintaining a maximum CPU and I/O activity at all times. It is free software to download and use, but it requires some installation. It's not too complicated, though. So as you can see in our code example, we launch our jobs from a pipe operator. A pipe is that little red vertical line you can see, which passes standard output of the command to the left and pipes it to the standard input of the command on the right. So in this case, the list of paths retrieved by the grep search in the mount, looking for mount is piped to the sort U, which removes any non-unique paths from that group. And then it pipes that again into the parallel command. And then parallel takes 16 file paths at a time, launches 16 Python scripts. And the curly brackets at the end are where each individual path from that list is passed to all 16 different script launches. If you're unsure how many jobs you might want to push through to your computer, you don't have to use the jobs command. Parallels max jobs flag along with the load flag will help you help the software kind of work out how many jobs it should run itself. And that checks the maximum free memory and the maximum I/O limit and the CPU usage of the computer that it's working on. It's really helpful if any of these are a limitation in your workflow to let the software do it for you. It will prevent encoding jobs crashing because any one of these, if any one of these exceeds the point of no return, if you like, then it will just drop the jobs down for you. It also maps job progress and includes a list of complete jobs so far. It's usable for Unix systems. I think it's a little bit complicated to install for Windows, but you can install it using git bash by enabling the Windows subsystem Linux feature. Okay. So next, we're going to look at the Python scripts. I thought it might be helpful just to quickly give you an overview of a few features in the Python scripts in case you go to look at the repository that you'll come across. They always start from line 1 with the Python shebang. So the shebang tells the Unix command line shell where to find the interpreter for the language that the script needs to run. It has to be at the very top of the script. We don't actually use this feature to load any of our code, but it's there in case other people need it. Below the shebang, I always have a detailed comment section. It's very detailed. So I put all of the way the script works into that comment section there, as much for myself as for my colleagues, because I don't always remember what the script does, and when there's 50 scripts, it's really helpful for me to review it. Next, you'll always find that the imports come underneath the notes for many of those of the Python standard library. So we've got OS, which is the operating system package for directly communicating with OS. Sys has system-specific parameters. The JSON import is the encoder and decoder for JSON file conversions, which turns them into a dictionary, which is really useful in the code. There's also shootil, which is a shell utilities that helps with file operations like copy and remove. Logging, which is the Python module that helps create script logs when reporting, and different levels such as info, warning, error, or critical. Subprocess, import subprocess is a really valuable Python module which we use to spawn new processes and connect to their input and output pipes to obtain return codes or outputs. I use this subprocess module a lot for FFmpeg and for media area tools in the code. So there's also a local section where I import a module that I've written with underneath it, I think it says, yeah. So that's a local module that I've written myself that I import underneath the global imports. So under the imports is the global variables, which I use across all the scripts. So they're best displayed in capitals so that I can differentiate them from local variables in the code. And they're variables that I need to use all the way through the code. So I put them at the beginning, capitalized in that way. These ones are just our secret key, kind of like environmental paths that link to our storage paths, so H22 paths and our QNAP storage. So the next block is usually the setup for the logging module, which you'll see. Here you're configuring your logging by giving the logger a unique name, creating an output path, setting formatting with date first, then log warning level, etc. And here next is a list of the different scripted functions I've written for the FFE1 to V210 script that the main will call. So main is the main function that actually drives the whole activity of the code. So they're folded down at the moment, so you can just see the list of all the names. But they include the check control function, which is present in most of my scripts, which I described earlier as part of the downtime control JSON system that we have working across all of our servers. Then there's the get color, which is going to use the FFV1. It's going to use media info to get color information from the FFV1. Get interlace is a small function that gets the interlacement information, again using media info through the subprocess. Change path, which controls the different path outputs that I need for the script. Create FFmpeg command is usually a pretty large function that handles all of the different FFmpeg flags that I need to create. Conformance check uses media conch with subprocess again to check that the finished FFV1 Matroska, no, V210 Matroska matches our policy for that. And there's a make MD5 function which handles creation of MD5, frame MD5s for both the FFV1 and the V210, so that we can do those lossless comparisons again on the flip side of this for the V210 conversion. Diff check manages the checking of the frame MD5s, and then we've got a failing log, which just outputs any failures that we find. We'll look at these a bit later on in the code. You'll also see for most code that at the very end of the script is a name main idiom shown here. This protects the script from being run accidentally if imported as a module into another script. It only allows it to run when the code is called as a standalone script. So I nearly always name all of my scripts in this way and have a main function which drives all of the activities of the code. Okay. So, lots of code, by the way. I should have forewarned you that this was going to be mostly talking at depth about code. So our shell script has now launched our Python script, and there are 16 of these running at once. So let's see what steps each Python script makes against each single file that's supplied to it. So we're looking at the main function, which I said earlier drives all of the activities of the script. So the first action is to create a logger list, which collects log messages during the script run. Because we've got 16 parallel scripts running, and one log really that captures all of the information. I don't want the various scripts to trample one another and for all the messages to get mixed up so it's not clear which log message is referring to which file. I tend to gather the log messages throughout the script and then push it once at the end of the code. The script starts with a log output, checks the downtime control restrictions, and then it uses something called sysargv to extract the file path that's been passed into the script at the moment that it's launched. So that's one of the arguments passed into the code from the shell launch script. It ensures that the supplied file is named correctly, and then it extracts the metadata from that FFE1 file to build the ffmpeg command. It then runs 2 checks to make sure that there's no files that have come through that don't start with an n underscore or that have mkv in the path. If either of those exists, then the script exits at that point. So where you see the set field equals, you're creating a variable here that will be populated by the results of the get interlacement function, which is just shown here. This function uses that subprocess command, and it calls media info, and you can see the media info command at the top. It's been broken into sections which are within a list, which subprocess requires you to supply the command in list form. So the media info command is then called by the subprocess check output call. The response is captured into the interlacement setting variable, and this variable is then converted from bytes string into a UTF encoded string. And then later on, the content of that string is checked to see whether there's TFF, BFF, or prog been returned from media info call against the FFE1. And then this is converted a bit lower down into a lowercase version of that same version. So TFF uppercase is how it's received from media info, but for the command to work in ffmpeg, it needs to be TFF lowercase, where it's inserted into the command later. So that's what that conversion is managing. Next, the color data variable is populated by the getColor function. In the same way, subprocess is used to call media info twice for the color primaries and the matrix coefficients colors. It converts the media info responses into ffmpeg compatible versions. For example, the BT.709 uppercase is converted into BT709 no dots lowercases. And these 2 bits of color information are then passed back into the main command. Next, the ffmpeg data is sent to create the ffmpeg command. I'll skip one there. Okay. And this function builds the ffmpeg command for us. Here you can see that each section of the script is given its own, each section of the ffmpeg flag is given its own small little list form, and the supplied ffmpeg data that we've passed into this command is then populated into the color building block and the interlacement block. And the style of breaking the command up into smaller pieces in this way, it's not really necessary at this stage to do it in this way, but because I have other scripts that work with more complexity, which we'll look at later, I tend to break all of the different ffmpeg flags up into their own little groups and name them. So then a neat version of this command is printed to the log, and then using the time module, we capture the start time of the encoding, and the ffmpeg encoding is launched using the subprocess call, and then this is written in try except blocks to make sure that if there's any exceptions with the ffmpeg call, that those are caught and the logs are updated to say that there was a problem with the file. And then at the bottom there's a TOC, so I've got tick and TOC. The TOC marks the completion time, and then there's a little bit of a sum to work out the seconds from that difference in time, and those are printed to the log to give us an overview of how long all of our transcodes are taking. So the transcode is now completed, and the script wants to ensure that the new v210 MOV is identical to the FFE1 Matroska. So again, timing the function, we make the frame_MD5 using the frame_MD5 function. Let me see if I can pull that in. There we go. So the function calls up the change path function to get the transcoding path for the FFE1 file. Then it builds 2 new path names for the MKV and the MOV framemd5 files. And it outputs those for the outputs for the framemd5s that are made. The very long lines of code that you can see there, we're going to look at those in the next section. They're a fix for an unexpected problem that we encountered when we were trying to do framemd5 checks from FFE1 Matroskas to V210 MOVs. So this sees completion of the timing and the lists there. So the MD5 TikTok, make MD5, it gives us the times and we output that to the log2. The separate framemd5 files are checked then with the diff check function. Uses subprocess to capture the response of the diff command. The sudo is a prefix that we use just to make sure that admin privileges are supplied to the diff file so that we can ensure that we can get a response from it. Sometimes we had a few failures depending on the storage that we were using. It has a conditional statement then to check if match or fail have been returned into the string, and those are passed back to main. So now we have a check which makes sure that match is in the result, and the match is confirmed in the logs for successes, and the framemd5s are moved to the framemd5 path global variable. Next, a block creates a whole file md5 checksum, generates the path it needs for the transcoded file, then makes the checksum. Okay. If you recall, we had one import that was for the Python script written to the make checksum. This is where it's executed, and this is the shortcode it launches for that. Oh, I've lost my way a little bit. My apologies. So anyway, the next step is for the checks that the checksums are valid. So it's making a whole file checksum for the file, and it makes sure that the checks are valid. And then the cleanup function is triggered. This cleans up the function responsible for calling up the media conch policy for the V210 MOV to check that the file matches the metadata requirements. Let me see where that is. Okay, that's there. Oh, I've got too many pages. It's too complicated, this script. It doesn't bear well that I get confused with it when I write these things, does it? You can see why I put so many notes and everything. So for the framemd5 matches, the script ends here, but for those who didn't pass, the else statement starts a new process. Okay. And that's at the bottom there. Okay. So I've fuzzed over that a little bit, I apologize. But so the framemd5 manifest paths are created and prepended failed. If they fail, the framemd5 failures are moved to their failure path using the shootil copy. The FFE1 Matroska file is moved to the local framemd5 failures folder path using the shootil move, and the V210 is moved to the failures, and then the logger list is written output. So hopefully you got some sense of how the script works there. But I want to get on to the more important thing. Problems we have with the lossy buffers in our files. Our lossless conversions from V210 MOV to FFE1 Matroska threw up some problems a couple of years ago for which we couldn't really find a solution ourselves. The framemd5s weren't matching for any of the video frames despite our repeated attempts to convert them. Thankfully, a short conversation with Dave revealed the potential solution in the Apple technical document TN2162, which he was kind enough to explain quite clearly to me. He suggested it could be a problem introduced by the capture card technology when the video was first created as a V210 MOV. It outlines in this document mapping and coding schemes for QuickTime files developed from digital video industry specifications such as REC ITUR BT601-4. For this example, we looked to scheme B, which you can see here. Y is an unsigned integer, CB and CR are offset binary integers. Certain Y, CB, and CR component values are reserved as synchronization signals and must not appear in a buffer. So according to Dave, for 10-bit video like those tested by our scripts, These buffer values are 0, 1, 2, 3, or 10, 20, 10, 21, 10, 22, and 10, 23. So the document continues that the writer of a QuickTime image is responsible for emitting these values, and the reader of a QuickTime image may assume that they are not present. So according to Dave, who's in the room, so it's very weird to quote him, the remaining component values, so he's gone, 4 to 63, 961 to 1019, for n equals 10 bits, accommodate occasional filter undershoot and overshoot in image processing. In some applications, these values are used to carry other information, e.g. transparency data. So I'm just going to try and explain that in a way that I understand, so hopefully you'll understand it as well. The videotape is captured using the capture technology, like Blackmagic cards, for example, as an uncompressed V210 MOV and saved to local storage. From here, it's converted to FFE1 Matroska and moved to our long-term storage. A year or so later, we retrieve it from long-term storage, convert it back to V210 using FFmpeg for dispatch to our regional archives. So the video files created are shown here. Let's imagine them as binary frames from the video file. This is what the buffer area might look like according to Apple's technical standards. And this buffer shouldn't have any data written into it for the Apple V210 MOV. So FFmpeg follows these guidelines when creating an Apple MOV file, emitting signals within this value range, the red line. But for the FFE1, this isn't the case, as it's not beholden to those technical standards, and so there isn't this limitation with the FFE1, so data is written into that buffer. This wouldn't cause a frame-MD5 problem between our FFE1 and V210 FFmpeg transcodes on the right if the capture technology had respected this Apple restriction as well. But certain capture card technology, Blackmagic's being one of them, they don't follow these guidelines specifically, and so these buffer values can be populated with information. When FFmpeg transcodes the V210 into the FFE1, they remain lossless, but when the FFE1 is retranscoded back to the V210, it correctly assumes that these values should be empty and compresses them, so they become lossy. So this becomes a problem when you run a frame-MD5 comparison with the raw video conversion. You have lossy converted sections in the V210 frame-MD5 and lossless converted raw video sections in the FFE1 frame-MD5. So if, as with my scripts, a positive frame-MD5 comparison signals a successful transcode, then potentially with an issue like this, you face a lot of repeated transcoding attempts that are actually false flags. Thankfully for us, Dave not only explained the solution, but also provided amendment to our frame-MD5 commands that you can see there with that really long YUV LUT trim, which actually removes that buffer section of the video frame. And that allows us to compare the data within the frame, excluding the buffer, to convert those sections only into raw video and compare only those pieces. And that basically got us through the frame-MD5 mismatches problems, and we were able to match most of our files that were failing before that. So thank you, Dave. For everybody at the BFI National Archive is very grateful for this fix, and it's being used daily. But I wanted to share it really because it's hard to make it legible, so I thought a graphic might help, and it's a really important thing that more people might fall foul of in the future. So we don't have scripts specifically written for FFE1 conversion to ProRes, but I'm going to share with you a command that we use quite often in our team. So FFmpeg-I calls the FFmpeg command again and supplies the input file. We use the map0 to map all the streams from the input to the output file. Here we use the codec for the video stream, and ProRes KS is, I believe, one of the best ProRes encoders for interlaced and Rec 709 support. We select profile V3, which selects ProRes H422HQ. I think 4 is 444. I can't remember quite how the others sit. Then we have chroma subsampling set for YUV422 with 10-bit a little endian. Then we have a codec copy again. We're very lazy with our audio at the BFI. We just copy it across all the time. We're very happy with PCM 16-bit. So we copy the audio codec straight across. Here we've got vendor AP10, which selects the vendor as the Apple or AP10. And I believe that helps with viewing in some video players, QuickTime Player amongst them. Not entirely sure if it's really necessary, but we put it in there anyway, just in case. Then we use the flags, the plus ILDCT, which ensures the output has interlaced field encoding. Then we pass those color primaries through, because if we don't pass those color primaries through, then they're not in the finished file. So you will have slightly poorer metadata for the color information in your ProRes file. And so we pass all three in. Now they're exact matches of the color information in the FFV1 Matroska, obviously, not just kind of guessed items. Then we select mob flags fast start, which ensures metadata for viewing before download is moved to the start of the file, so it buffers basically in playback. And then we select the output file. And the same for our FFV1 to H.264 conversion. We don't really have a specific transcode script for it, but we do have a kind of some FFmpeg code that we use. Again, FFmpeg-I in the input. We map 0 again, everything, so that we ensure that all the audio streams are there, basically. We select the codec for the video stream as libx264 for the H.264 codec. We set CRF 28, which is a very low CRF, considering, but the range is 0 to 51, available for chrominance 420p, I believe. The default in FFmpeg is 23. We did a bit of testing and we found that 28 was about as high as you could go to see the most compression against a file without it being visually obvious, and also gaining the most space-saving options for us. So 28 was our choice. We have PIX format chroma subsampling for the YUV 420 with 8 bits. We use video filter YADIF, which is yet another deinterlace filter, which is a great name, to make it progressive, which we find is essential for MP4 files because they're mostly supplied through computers. And when people watch interlacement on computers, it's quite confusing, I think. So we always make them progressive. We have, again, the copy. Oh, no, we're actually converting the codec on the audio here. We're selecting the AAC codec. And we are having that mob flags fast start again to make sure that the metadata is viewable immediately with buffering. And then we have the output setting at the bottom. There isn't a good alternative MP4 transcoding script on the FFimproviser website. I don't know if you're aware of it, but Amir Open Source have an FFimprovisers page, which is brilliant for supplying preservation FFmpeg commands. And on there's a nice H.264, H.265 transcoding FFmpeg command, which uses the GPU, so it's possibly a quicker way to transcode. Okay, so just a quick word on our FFV1 capture card technology. A recent development for the BFI is to fund, along with the Norwegian Film Archive, the development of an FFV1 codec capture card technology. It's already being used in our digitization suites, the Bluefish Epoch Supernova CG card, used in conjunction with Bluefish's Ingestion software. It's reduced a great deal of transcoding energy in our servers and makes moving files to long-term storage much quicker. Bluefish is proprietary software, but because it's capturing such an important archival FFV1 standard, I think it's worth sharing here at No Time to Wait. We now capture most of our videotape direct to FFV1 Matroska thanks to this development. We use HP Z8 desktop workstations for this capture. We have the machines using SSD or HDD media drives, which are striped RAID 0. You get pretty good storage on those. We run each workstation with 2 cards, providing 6 inputs in total. So the Bluefish cards can be flashed to be all 4 connectors, 4 inputs or 2 inputs and 2 outputs. We don't use the outputs at all, so we have 6 inputs instead. which means 6 concurrent captures on any given workstation. So we run 3 digibeta workstations concurrently, 2 cards in each, so therefore we're getting 8 videotape captures concurrently throughout the day, 18, sorry. But just to balance things, we have also, oh, gone too far, the wonderful software built by Dave and others, vRecord, which is an excellent option, I think, for capturing to FFE1 for those who aren't doing that yet or want to know more about it. It has some amazing preservation features, which includes digitization logs being embedded into your Matroska wrapper if you select FFE1 Matroska, and also a choice of FFE1 codec that you want to use, like the slices that you need. It's just got, everything is just sort of built for the preservation archivist. So I think definitely take a look at vRecord if capturing 1 file at a time is adequate for you. And just a note about FFE1 Matroska workflows at the BFI. We do also do a lot of work with raw cooked. I've spoken about it a lot, and I'm aware that today there was Jerome's raw cooked presentation workshop on as well, and I didn't want to duplicate content, but we do have a lot of scripts in our DPX encoding repository, which is our raw cooked workflows, basically. So we use FFE1s there for all our 2K and 4K film preservation of RGB and Luma Y films, captured in-house, and also our legacy film projects. This software standard has saved us a lot of space. Potentially, I think one project alone saved us about 1.5 petabytes of data. We use the attachment feature that comes with the Matroska file to store lots of additional metadata about the original DPX sequences and their sequence structures, etc., in that Matroska file. It's an amazing tool, and I'm not covering it specifically today, but any questions which we have time for now, I'm happy to answer. So thank you.
I have a microphone, so I can pass it around for any questions for Joanna. Hi, Radoslav.
Hello, I haven't understand which hardware support vRecord, which seems to be maybe the at this moment best tool, best open source tool that can capture in a good shape the material. So which hardware support? I know for DV, but which rest?
Hardware as in server workstations, that kind of?
No, capture hardware.
Capture cards, that type of thing.
Because I see the Bluefish, but I'm afraid that FFmpeg doesn't support Bluefish, support only SDK from Blackmagic. Even Edge are not supporting, which is a good thing, and I will propose next days, if BFI want, to support the old Adrenaline and Mojo from Ivid, because there are a lot of those second-hand which are very cheap, very good for preservation of video materials, but Avid doesn't more care about them, have no documentation, don't sell software, etc. So we can reuse them as a hardware capture on FFmpeg. But right now, in this moment, which hardware it supports? Thank you.
That sounds really interesting. Unfortunately, the decisions for hardware capture, setup, configuration all sit within a different department to the one I'm within, and so I don't have the information for you on that, I'm afraid. We just process the files once they are passed through to the Data and Digital Preservation department, and that's really why the code and the conversions using FFmpeg is the area that we think most about. Bluefish was already established in our videotape capture workflows, so adding FFE1 to that was an easy and obvious choice for us to move the FFE1s into our workflows more quickly and easily than going through a processing, transcoding processing phase. But I would definitely recommend also vRecord, which is an excellent tool as well, and uses FFmpeg if FFmpeg is what you want to use for your conversions.
I had just a question about being a GitHub repository manager at BFI. I was curious if you were aware of any other institutions using these scripts, and if there were any external contributions that helped support them?
None at the moment. The idea frightens me a little bit because this is my code and I might have put some bugs in there, but we don't have anything at the moment. I mean, the DPX encoding, we've had some inquiries and we've had some institutions who have forked them and I believe are using them, but haven't had any recent updates. So it's all quite, I think because they're not agnostic and they're not easy to install and use immediately, they're probably not going to be everyone's first choice, but I'm hopeful really more that people can read them, look at the functions, look at the way we do things, and learn as new developers ways of actually using the tools to build their own kind of tools, if that makes sense.
Cool. More questions? I'm going to take a while to get back there. Hang on. Pass it down.
Thank you. Yeah, from the GitHub we can learn things for other field because I'm in software preservation, so I'm not dealing with video files, but with softwares and disk images. So thank you for the GitHub. And I just was wondering about the context. How long did it take to develop this? And did you had an extra budget? Because yeah, we want to develop things like this for checksum and for conversion of disk images, but we are two. And we don't have the resources. So I was thinking, can you explain the context in which you could develop all of this? Thank you.
Yeah, absolutely. When I was first taken on at the BFI, I was in a Heritage 2022 position, so my job was to kind of govern the DPX conversion to FFV1 specifically. My boss, line manager Stephen McConaughey, managed to find budget for a developer position. And I was lucky enough to get that post at the BFI. And I think once the developer position came into being, suddenly there was resources to start building these workflows. To build a script like the transcoding script takes maybe a couple of weeks. Researching the scripting, having some understanding of Python already helps with that. So many of the scripts that I write use the Python standard library. So we're not using a lot of packages or external things, we're just using the standard library to work through them. And then sub-process to work with these amazing open source tools. A lot of the servers already have these open source tools installed on them, so implementing the scripts onto the servers isn't too challenging for us because we use media area and FFmpeg really everywhere in our workflows. It's all through all of our servers. So it's not too complicated if you have someone who can write the Python, and if you have team members who understand the way, maybe if we're using APIs, for example, understand the way the APIs are set up and configured. That's probably some of the bigger research is like working with third-party kind of like CMS systems and that kind of thing. Simple transcoding scripts, not too complicated, with a little bit of research. I hope that helped.
Thanks. You said something like 100,000 programs went through those code, actually, which really is a lot. And my question is that everything that went into the archive, or or do you make different? Do you have different workflows and scripts for in-house digitizations, born digital stuff that comes from outside, and so on? And how does that affect your scripts and your workflow here?
Okay, so that 100,000 was just one of our projects, the Heritage 2022 project, which I might look to my colleague Lucy in a minute to expand that a bit more. The 100,000 are items, so they're program items. Sometimes we have multiple items on one tape, so it would be the capture of one tape. And then we have a series of scripts called the splitting scripts, which take time codes from an associated item record kept in our database, which has the cut times in them, and FFmpeg within our splitting scripts then splits that up. So the 100,000 might not literally have been 100,000 individual captures. It might have been like a third of that possibly, or 2/3 of that, and then the splitting kind of process that at a later date. Alongside that, we have other videotape capture workflows. So we have an Ofcom workflow. We have capturing 1-inch videotape. I think 1-inch is quite endangered, so we've been working through all of our 1-inch collections at the BFI. Have I missed anything else, Lucy, on that? I think that's it. So yeah, this script is just an H22 script that I showed you, so that was just working on those 100,000 as far as I'm aware. But we have versions of that script that work on our business as usual transcoding conversions. But now, of course, we've moved to Bluefish capture, that these transcoding scripts are generally being kind of put to bed now. They're not so necessary for us.
Any more? Peter?
Thanks. I was wondering, are you using the FrameMD5 just for integrity checking of the conversion? And have you considered stream hash in comparison?
No, we have not. No,
Because in the past, we only had FrameMD5 to do that.
but now there are alternatives.
There's something where you get one hash code per stream, not per frame.
Oh, I see what you mean. Yes, so you get like an MD5 hash of the video stream entirely, and then an audio stream. I actually just read a blog about that recently. I think it was Bay Area Video Coalition, Morgan O'Morrell. I saw that he was doing that with one of his conversions, and I flagged it in my mind, but I haven't come back to it yet.
Because I was wondering if you run into errors, do you actually look at the FrameMD5s and see how big the impact is, or do you just go like, it's not clean, just reset it?
We do have to evaluate them quite often, particularly now we're coming towards the end of the project. We have like our exceptions workflows where we're getting a few little anomalies coming through in the captures. We do have to analyze them, yeah, and when we can work out what it is. For example, sometimes we have audio offset to the video, and when we transcode that from V210 to FFV1, then the FFV1 gets extra video frames at the beginning, and so you have a mismatch there because there's like 0 stream additional checksums in that FrameMD5 that aren't in the V210, for example. And so yes, when we do tend to just give them an overview and have a look at them and have a little discussion about what we think the problem is, and then we just try a couple of little homemade FFmpeg conversions to work out if we can fix it ourselves. And yeah, there's not too many, thankfully, that we have to do that with, because that's quite time-consuming work, obviously.
Okay, but you do... enough, later. Thank you.
You sure? Later, let's definitely talk about that later.
Yep.
Just curious about the color tags you showed earlier in the different transcodes, especially about the color trace one, which was set to BT709. Now, depending on the capture cards, for instance, I've noticed that sometimes you get different values, like the one for gamma 2.8, for instance. So it's not always consistent, especially if you're working with different vendors. So did you run into this situation, and if you change the value, did you have a way to log that, for instance? Since,
on a file-by-file basis, we're just at the moment, we're looking for, we're about to build a new kind of premise-based metadata tracking system so that we can try to track events that happen in the transcoding changeovers in our files, so that we can map any differences or changes that we have happen to the files throughout the transcoding processes. We don't at the moment, but we do keep logs of the transcodes, etc. So we do kind of have a loose way of tracking that. With regard to the color trace, BT709, I think we hard code that into all our scripts. And I'm going to look at Dave now because I think that he maybe recommended that to us. I'm not sure. That was a conversation my line manager had. So BT709 is our standard, I think, for any SD color trace information. Okay. I think I'd like to have a chat with you about that later, if that's okay.
Joanna, I wanted to ask, like, I might have been out of the room when you were talking about this, but for all the sharing you're doing of the scripts and software that you're running, have you had much of a chance to share much of your recommendations for the hardware one might need if they're transcoding mountains of DPX files or FFP1s? Because I imagine there was a lot of sort of experimentation and lessons learned in trying to pick out what computers, servers, and stuff you were doing.
That, again, a lot of that work was completed by my line manager, Stephen McConaughey. He, I think, did a lot of research in that area. When it comes to DPX, I did create a cheat sheet last year for how to optimize your computer to do efficient DPX raw cooking. So there was parallelization information in there and just talking about how CPUs, more CPUs you've got, basically the more threads you can get and the faster encoding you can have. So there is some documentation that we've put out, but no, probably not as much as we could do. I should say that's something we could develop a bit more, David. Definitely. if there's no more, shall I move on to this part 2, which is the media asset management retrieval? Replacement? Great, thank you ever so much. Those were great questions. Sorry I lost it there a little bit in the middle. Okay, so in March 2021, Head of Data and Digital Preservation, Stephen McConaughey, made a tough decision to decommission our existing media asset management system, or MAM, and build our own custom replacement for this. My role was to build all the back-end tooling for the project using Python. With Stephen's experience and guidance, as I'd only really been in post 6 months when he decided to do this, his overview of it, his understanding of it, and his assistance was really essential. So, where was our media asset management system positioned, and what did it do? Across 20 network shares, we have automated ingest folders where newly created files are placed once they have been manually or automatically documented in our Axial Collections AdLibs collection management system, which the BFI National Archive call Collections Information Database, or SID for short. So SID records have been made of the files have been captured, digitized, converted into their long-term preservation formats, and they've been named after their object number from the SID item record. When our colleagues have created these, then they are renamed manually and placed into the auto-ingest folders, which then it executes a validation check against the file. So we have many paths for this. We've got DPX encoding, off-air TV recording. These are all moved in through automated processes. But then we have more manual processes that also feed into these. First thing that the Python script checks, we've got some scripting originally, it was auto-ingest scripting that was written by Edward Anderson, that was written in legacy Python 2 code. It would validate the files once they made their way into the auto-ingest folder subsystems. And it would check a few vitals, so like the name was formatted correctly, that the item linked correctly to a SID item record, that the file type was recognized from the extension, and that it matches the SID item record, and that the file hadn't already been ingested, so it would run a check for that. And that the item is being ingested in its correct order, so 1 of 2 is before 2 of 2, and that kind of thing. So once our Python code had finished that validation, it would initiate the ingest phase using Imogen's API. Now, Imogen is the media asset management system that we look to replace. Ingest would occur one file at a time. So your FFE1 file, for example, would be separately ingested to the WAV file and to the DPX sequence, which would be tar wrapped, by the way. This block sees many integrations between the Imogen media asset management system, the Spectralogic Black Pearl software development kit, or SDK, which is how we write our data to the long-term tape storage. And it would also integrate with the Python codes in there too, and the Axial SID records. So basically, Python initiated the ingest, which enabled Imogen to move the files to Spectra's Black Pearl tape library, and added the file into a lock, which prevented any further actions being taken against it by the Python coding. So the Imogen software provided really useful visualization tools to view how far through ingest the files were, which allowed for good throughput analysis by our teams. Once ingested, the legacy Python script persistence.py, which was also written by Edward, would verify for the BFI National Archive that the file had actually made it into the Black Pearl data tape library by comparing a local and a remote Black Pearl file. So it would download the download the MD5 checks from the Black Pearl, and then build a local MD5 checksum as well, and ensure that they were identical. It also compared the file sizes as well, and then outputted the successes to our logs. So the next stage, now that the files had persisted, it was possible to use Spectra's Black Pearl Eon browser to access and download the files, which spoke directly between the Black Pearl tape library and has a user interface for individuals to use. It's a bit like a GUI that is not unlike an FTP download software. So the next stage saw Imogen create proxy MP4 HLS video files and proxy audio files and proxy image files for stills, so that documents or applications wouldn't go through this stage, but it meant that we could view those files. When these proxy files were created and linked to the newly created SID media record, generated again by Ingestion, that links it to the SID item record that it represents, at this point they became viewable to all the BFI staff who had access to our digital preservation infrastructure through Ingestion's media asset management software. It had an integrated video and audio viewer within it, and also some useful video editing software. So the final stage would be then for our own Python scripts to read the persistence checks, knowing that those checksums matched and that the file had persisted successfully. It would then look to see that all of the transcoding had finished by the removal of that lock state on the file. And at this point only, our own Python 2 scripts would delete the original asset, knowing that there was a valid copy. So now our system looks... Okay. Some notes there that I don't need. So to summarize Ingestion's involvement in this workflow, it would supply ingest confirmation to Axial's AdLib SID records and also create digital media records within our SID database that confirmed a digital file had persisted to Spectra's tape library. Next, Ingestion managed creation of proxy MP4, HLS, audio and JPEG thumbnails and fed back the names of those into the SID digital media record. Ingestion would then communicate directly to the tape storage. Spectra's Black Pearl S3 is a native HTTP-based interface to our long-term storage. It enables easy archiving of data to tape library, and it also offers extra services where you can write to servers or to cloud solutions as well. But we just use the tape library as far as I'm aware. It has a REST-based HTTP API. An API is an application programming interface. That allows client software to manage bulk storage, read, write, and delete operations. However, Ingestion limited our write to magnetic tape libraries to a one file at a time basis, using the connection it had with Spectra's S3 software, which provided pretty easy communications between the two. The problem is that we could only send one file at a time, so the Ingestion to Spectra integration was increasingly unable to meet the demands in our growing ingest workflows, such as our 100,000 videotapes. This was also probably a consequence of our ongoing videotape off-air TV recording systems, which create about 500 MPEG-TS video files a day, and an increase as well from 2K to 4K film transcoding with our raw cook pipelines too, which just makes much larger files. So with Ingestion removed, we now have a lot of space. And this is kind of how things are organized today. What's happened? Was there a color background come in there? Okay. So we deprecated the script called persistence.py, and it's been replaced by some of the new coding. The ingest, persistence and access copy creation are now all managed by Python 3 scripts, which I've built. Also the validation and delete scripts in auto-ingest.py, which was Edward's Python 2 script, have been refactored and moved into Python 3. The scripts now all deal directly with the Axial API, so creating and updating SID item and digital media records, and also the Python scripts speak directly to the Black Pearl SDK, so we can write our own tapes, our own information to bulk ingest in the tape libraries. We lost Ingestion's progress reporting, unfortunately, but Stephen quickly built an Elasticsearch log monitor with the Kibana visualization tool that lets us view ingested files by file type, by date period, by groupings, etc. This is our ingest for 2023. 28,000 files were ingested in January, with the majority being MPEG transport streams from our off-air TV recording. It breaks the collections down into groups in the top right, genres and subjects below that. This can't report on problems with ingests, but we have an error reporting feature implemented in our logging that gives auto-ingest users that feedback. So I hope to move our scripts into Apache Airflow scheduling and monitoring platform at some point in the near future, which would also give us a more granular error reporting via a web UI format, making it easier for the data and digital preservation team as a whole to monitor the script activities that are going on across all of the servers. We're also aware, since this has been set up, that Elasticsearch is now no longer an open source tool, sadly. But I believe it was when this was first written. But I just thought I'd add that here. So we recently lost functionality of the Eon browser downloader, which Spectra Logic supported. So instead, with Stephen's help, I built a Python Flask web app UI to allow BFI staff with access to DPI to download direct files from the Black Pearl to folders of their choice. The first version was built using SQLite with a SQL database, and a later version that's just been completed uses the Elasticsearch again, which allows integration with the DPI browser, which is the final phase of our replacement of the Imogen project. It's being built at the moment by colleagues in technical and digital transformation at the BFI, who are ensuring authenticated access to all the DPI collections. And their web interface will provide replacement for the video player that Imogen used to supply, and also link to the DPI downloader functionality, which I built as part of that web interface. I should add that when Imogen was taken down in 2021, Stephen quickly put together a temporary stand-in video player, which used, I think, Nginx to stream HLS videos, and also implemented the IIIF image viewer as well for viewing image collections. So we haven't been without an option for viewing things. So this new Python code is what I want to look at more closely next. I'm thrilled to say we've just open sourced all of this code to our latest GitHub repository, which you can see here, the BFI_scripts. It works, it's a work in progress, so it's still being kind of moved over at the moment, and descriptions are being changed in the README quite continually. I want to thank the BFI National Archive for allowing us to make all our code available. Not everybody's that brave, really, but it does align with our Screen Archives of the Future 2033 strategic goal to be the world's most open and accessible archive. So it's wonderful to have that support to open source our codes at this stage. So there's 6 kind of main scripts that we have that replace that media asset management system. And they carry out the bulk of the DPI workload. It's a lot more code, so bear with me as I go through it. To begin with, it's good to just give you an overview of where all of these scripts kind of interact on all the different servers across storage across the BFI. We have like an auto ingest folder where the media asset management tool used to work within this auto ingest folder, and it's had some developments in there recently, and there's extra folders have been added in. But this is the layout for our auto ingest folder shares in all of the storage. There's an auto detect folder, well, there's an ingest folder really where people put the files initially. In the ingest folder is an auto detect folder which will accept any file format and process that. But there are also more specific subfolders for people who want to put them into video specific or image specific or proxy folders. You have a current errors folder which contains that error reporting that I mentioned earlier. It has a CSV with each day's errors listed in there and a description of what the error might be. And then the 3 orange folders are where my new automation scripts work. So from the ingest folders, files are moved into the Black Pearl ingest folder, subfolder, and then when ingest is completed, they're moved to the transcode folder where the proxy copies are made, and then when proxy transcoding is finished, they're moved into the completed folder where the auto ingest script picks them up for deletion. So this is our auto ingest Python 3 script with some changes that have been implemented since it was created by Edward. It collects up all the log messages for files in scope for processing. So it doesn't look on a file-by-file basis. It goes through the logs to find files that are still not completed, and it works through the logs to actually access the files on the servers. It then iterates all the auto-ingest folders and searches within each path, within the completed path and within the ingest paths. If it finds files within the completed path, then it checks the logs for persistent confirmation, and if it finds that persistence confirmation, which means that those 2 checksums match between the Black Pearl and the local MD5, then it just deletes the file. And it excludes incorrect file paths or file names from processing. So if it comes across any files that have been put into the ingest folder, for example, that haven't been finished or named correctly, then it won't process those. It leaves them in place and puts an error into that current errors folder. It has some nice regular expression work in it, which I inherited from Edward. The first here is in the Czech file name, so it uses regular expressions, or regex, I call it, in this function here to search for just file names that have uppercase and lowercase letters in them, or underscores, or numbers, I believe. And if there's anything else, then the file name is rejected. There's also some rejects in the check part hole script, which is looking for a match of 2 to 4 consecutive numbers separated by an of, and another 2 to 4 consecutive numbers. This is our part hole, which we use throughout all of our file naming protocols, so that we know if there's multiple reels, for example, of a film DPX that's been scanned, 01 of 03, 02 of 03, 03 of 03. A later check examines the extension of the file name that's been put into the auto-ingest folder, ingest folders, to check that the file extension matches an agreed dictionary of accepted file formats at the BFI. So if this script finds a .mxf, then the file type in the associated SID item record can either be an MXF or it can be an IMP now as well, because we've just expanded to accept the interoperable master format package, which we're receiving from Netflix. So the checks continue with SID media record checks to make sure that the file hasn't been ingested already. And again, we check Black Pearl to make sure that there's no file on the Black Pearl with the same name. It's all belts and braces checks, really, just to stop us getting duplicates written to tape. Because we recently started ingesting Netflix files to Black Pearl tape library, we've separated our buckets so that BFI preservation bucket content is all stored in one bucket and Netflix is stored in another bucket. So quite frequently throughout these scripts, you'll see a reference to Netflix, looking to ensure that we're making sure that we're checking in the right bucket and we're pushing files to the right bucket as well, separations. So the next stage looks at whether the code is next in line for ingest or whether it's part within its part whole group. So for example, if 02 of 04 is placed into an ingest folder before 01 of 04, then 02 of 04 won't progress until 01 of 04 has progressed. This is the usual practice for all of our ingests, except when we have film scans where we have a folder called incomplete scans. And quite often with film scanning, they'll just re-scan one particular part of a reel. It might not be the first part, and they'll need to ingest that at a later date. So they have an incomplete scans path, which will accept any part whole ordering. If any 01 of 01 turn up, or any 01 of 02 parts, then they immediately get put through for ingest without question. But any later parts have to have the checks made against them. So before ingest is confirmed, 2 final checks are performed. One looks to check the downtime control JSON, which I mentioned, to make sure that the do ingest flag is set to true and that the auto ingest scripts are set to true, in case we want to just prevent ingest for any time and allow deletions to happen. The second check is that the full size of the file being ingested is under 1 terabyte in size. We're currently not able to ingest files over 1 terabyte, which is the maximum size allowed by Spectra's Black Pearl for a single blob of data in its storage. If we exceed this limit, then we can't run a whole checksum file against, checksum check against that file. So it kind of breaks our persistence checks as they stand at the moment. So we try to keep all of our ingest under 1 terabyte at this time. When all these checks have passed, then the file is moved out of the ingest subfolder into the Black Pearl ingest folder, and then the next scripts pick it up. So this is the script that manages the write of the ingest files moved into that Black Pearl ingest folder. It's called Black Pearl move put. They're not very inventive names, I have to say. My names are usually quite, quite specific and a bit obvious, but that's a good thing in coding. So what this does in a different way to Imogen is it allows for a buildup of files to be collected into a Black Pearl ingest folder, and it allows us to put up to 1 terabyte or 2 terabyte groups of files to the Black Pearl tape library at any given time, which allows us far bigger throughput of files. I think in the Imogen era, I need to double check with you, Lucy, I think we were seeing 1 terabyte maximum ingests a week, 1 to 3 terabytes a week, but now in this modern era of putting direct, we're seeing, I think, 7 to 10 put terabytes of put per week, with some exceptions that have gone up into the 20s, I think. 7 to 10 terabytes a day, thank you, Lucy. So that's really why it was essential for us to replace the image and put option, because now we can get a 1 week's worth of ingest in a day, basically. So this one script is launched multiple times from each of our auto-ingest shares. It's using sysarg to capture that launch from a shell script, and then one file path is supplied to the script. No, that's not correct. This one script is launched multiple times from each share, and the share is passed in as a sysarg from the cron tab launch, so it's receiving the actual auto-ingest path from the launch. Here you can see all the different shares in that larger block. The script user is listed, then the flock lock, which protects the scripts from launching multiple times, is also in that list, second piece along. We call the Python script using the py3env environmental variable, which is the virtual environment that's installed into the servers, which we install all of our Python dependencies into to protect the bigger ecosystem of the whole server. And then following that is the name of the script that we launch, and then after that you can see in comments the name of the actual server that the auto-ingest file is on, so grac47, F47 for example, at the top there. The last bit is capturing all the standard out and errors to a Python log, which is overwritten each time the script runs, but it's there as a fail-safe to catch any errors in the code if a problem comes up. So the script separates out the Netflix paths at this point, as we mentioned earlier, to ensure that the correct data is being supplied into the correct buckets and that we have that separation. The remaining paths are checked against an ingest config YAML to see what their maximum ingest folders should be. So we have a YAML document with the path, with the auto-ingest share in there, and on a storage by storage basis, we've kind of adjusted what our maximum puts are. Generally, it's 1 terabyte blocks that we work with, but on some of our older QNAPs, we've upped that to 2 terabytes where there's a lot of files being generated, just to save a lot of I/O communications. And for one, we have a rapid ingest, so I think we've just got like 200 megabytes on that one, so any file that's added into it is immediately put for urgent updates. So a few checks follow to ensure that the paths are present. So that means that the auto-ingest path can be found. You'd only lose that if a mount was dropped from the server that the script is running from. And then there's a few auto-ingest, Blackpool ingest path checks. They're saved into 2 variables in the folders, so they make sure that the file that they're finding within the folder is guaranteed an actual file, and that they separate them into, oh, there we go, no, I'm looking at the bottom. Okay, so at that point, once we're inside the auto-ingest folder, we build up a list of files within that Blackpool ingest folder and a list of folders within that Blackpool ingest folder. We'll see why in the next section. So next, the script moves to process folders first where no files have been found in the auto-ingest path, which means there are no files to move into the ingest folder. It only wants to deal with the ingest folders at this point, so it starts with check to make sure that the file starts with ingest. So extracting the folder name to its own variable, the script checks how old the folder is by extracting date and time from the folder name. So every ingest folder, when it's created, is given the name ingest underscore, and then the date of the moment that it's made and the time of the moment that it's made. It uses the check folder age function to see how old that folder is, so if it was made in the last day or 2 days. The date string is converted into a datetime object and compared against the time now. The put scripts don't automatically push files to the black Perl tape library. If there's not enough files moved into a new ingest folder or an existing ingest folder that's not a day old, then they don't collectively meet that upload size of 1 terabyte, for example, then the folder's left for the next pass to see if more files can be added, but only up to 1 24-hour period. So when it checks that time, if the time is older than a day old, then the ingest folder is immediately put to the Black Perl SpectraLogic SDK using the put dir function, which should be showing now. So we use the software development kit, the SDK, and they've got classes in there that are useful for really simple, easy interactions with it. So we use the helper class, put all objects in directory. So that allows us to push a whole directory full of items straight to the Black Pearl tape library, all in one hit. When it completes that process, the SDK will return a job ID for that job. So the job ID is then used to rename the ingest folder so that we have a changeover in the folder that shows that it's been put to the Black Pearl library. To create that JSON file, we use a different class here, the SDK client module, put job completed notification, registration, Spectra S3, which is a long one. And that sends a notification to a Flask app that Stephen McConaughey built a little while ago. And that's this bit of code here. I've not added this to our repository yet, but I will soon. We have it running continually on our server to catch these notifications, convert them into a JSON file, and dump them into our Black Pearl folder on our Isilon storage. It runs on our local server IP, and it uses port 5000, as you can see at the bottom. So again, if the file is under 1 day old, then it gets left there. Files can be continually added to it until it becomes a day old or until it exceeds its upload size. Finally, the script checks for population of the job ID, the job list, sorry, and if so, it renames the folder, as I just explained, from that ingest, but it's renamed to the job ID. So it does this using the path rename function. First, it checks if the job was split into more than one job. I've never seen it, but I've factored it into the code to make sure that we're covered in case more than one job ID is returned, for example, if it's split. So it checks multiples and then builds that folder name from those multiples. Okay. So now we'll look at what happens when the files are found. It launches a while loop. So this is the first example we just saw was when there are no files in the folder and we're just dealing with the ingest folder. Now we've got files within the Black Pearl ingest folder, and this is the loop that handles putting those files into an ingest folder. So it refreshes the folders variable to make sure that the list of folders in that Black Pearl ingest folder is as up to date as possible. It then iterates through that folder looking for any existing ingest folders. The script checks how large the contents of that folder is and saves that into a variable called fsize. And it uses this sum to iterate all the contents of a folder and add them into a final byte value. If this folder is under that 1 terabyte limit, then more files are added into that ingest folder until it reaches that 1 terabyte list, which is happening in, this script here. Okay. If smaller, then the file is, okay. I didn't get a chance to read through this, so I apologize. I'm just going to look at the screen. So the move to ingest folder, okay, this starts moving all of the files into the ingest folder and checking the status of the Black Pearl file, of the file first, to make sure it's not already been ingested into Black Pearl. There's always the risk, I think, that when you have folders that are in all the shares, that people might accidentally move files into the wrong folders. So we like to make sure that Black Pearl doesn't have a version already on there. If it does, it just skips the folder. Then it checks the folder size after if it's moved the folder, to check it's not yet over the upload side. If it's not, it moves the file into that folder, and then it keeps looping through that until that's completed. We also have the check BP status there. That's where it checks using the head object request for the SDK. Okay. So we have another folder size check. There's lots of folder size checks. I think when I refactor this script, there's lots of work I can do on not getting folder size checks so continually. The folder's then pushed to the Black Pearl library again using the put dir once it's reached that maximum size. Finally, it checks again for the job list variable, and if it found it, renames the folder with the job ID. It also checks if there are any files remaining. So if, for example, there's 200 files in the folder and it reached that 1 terabyte with using just 50 of them, then it stores the remainder in a files remaining variable, and that updates the files variable, which then informs the while loop to ensure that it keeps running. So it will launch again and then restart the process again, moving files into a new ingest folder. And then the logs are updated, and the script exits once it's reached working through all of those files. Okay, so I hope that gives you an overview of the put methodology that we use there. The next script is the Black Pearl validate make record script. Going to try and whip through this one quite quickly. So unlike the last script, there are just 2 scripts that work for this one. One solely for the off-air TV recording, because we have 500 files a day, and one for every other path that we have, basically. It checks first for the Netflix path and ensures the auto-ingest path variable is correctly named, adding it and all regular paths to the auto-ingest list. Then opens and reads the JSON file, which lists different bucket names with balls indicating which is the current bucket for writing data into Black Pearl. This is a manually updated JSON that we alter as and when we decide we want to start recording, moving files into different buckets within our preservation group. We had a bucket recently that got, I think, to 10 petabytes. It was very full anyway, so we've decided we're now going to start splitting it across preservation buckets in the future. The script next builds a list of folders found in the auto-ingest Black Pearl ingest folder. If none are found, the script moves out to the auto-ingest next path, so it moves on to the next path. It then iterates the folder list, and if any folders are found starting with ingest or error, then the script misses them. It's just looking for folders that are named after the job ID or that have a pending prefix on them, which means they've been worked on by this script already, but not all of the data has been available to finish processing the file. If a folder's found named after its job ID, then the script searches for that matching JSON file, which you saw earlier we're collecting from that Flask app and putting into an Isilon Black Pearl folder. This is the JSON confirmation created by the Black Pearl SDK notification that's sent to our Flask app. They populate a folder called Black Pearl folder on the Isilon. It opens and reads the JSON to see if any notification is given of a cancellation to that put, because sometimes when we're writing to the Black Pearl library, something can break the put process and it can be cancelled partway through, and that cancellation should pass through to this JSON file. It also has a failed files section within that JSON where we are hoping that we'll start seeing, if it happens, the file names of the files that haven't managed to persist to data tape. And this script, ready for that, extracts that information and will then move those files out of the completed ingest folder so that they can be put back through to a second ingest attempt at a later date. Then it launches a very big function called the process files function, which manages the persistent checking for the files left in the folder, and it outputs the success of this to a success variable. I'm just going to skip through these because we haven't got a lot of time. So, where are we at? So yeah, the same process happens again. We are going to work through the processing file function. So it retrieves the byte size of the file, it gets the duration in seconds and milliseconds, it writes the file name, duration, and size to a CSV, temporarily storing this information for all files with the intention of writing it into the SID digital media record at some point in the future development. That's that one there. It retrieves confirmation of write to the Black Pearl remote MD5, and file sizes are retrieved from the Black Pearl SDK. That's one too far, but if confirmation of the write to the BP is not confirmed, then the write warnings are put into the log to warn that a re-ingest is going to be needed. It checks the local MD5 has been retrieved from the local storage, so I have separate scripts that are making the MD5 checksums. If no local MD5 has been made yet, then it writes a warning and skips over the file again, and then prefixes the folder with the pending warning. It checks the byte size of the local file against the remote one in the Black Pearl, And then the final check is to check if the SID media record has already been created for that file, meaning it's already been through this process and so will have ingested as well. So it's belts and braces again, lots of checks to make sure that we don't get duplicate files written into Black Pearl and duplicate records created. So if all these pass okay, then a persistent message is written to the auto-ingest logs, which basically tells auto-ingest that it can delete the file at a later date. But before that happens, we need to move those files to the transcode folder for the MP4 transcoding processes. And I think at that point, I'm going to skip on to the checksum making script. So there's just one version of our checksum maker media info script. So this script creates MD5 checksums across all of the auto-ingest shares so that the comparisons can occur for the local and remote version scripting. This was one of the first things we outsourced to our own Python scripts because checksums were taking a long time to generate within the old persistence code that we used to use. So we've now got multiple iterations of the script running at any one given time. This is the shell script is launched multiple times from the cron tab of one of our servers. So it lists the auto-ingest paths that it wants to target on the right-hand side, and that number behind it are the amount of jobs that I want to pass in for that share to the GNU parallel. So it will launch, for example, some have 20 jobs running against them, and that's the store off-air TV recording, and also our Ofcom and videotape digitization has 20 parallel processes running against it. The main script is launched against just one of the files, so it just receives that one file path through those jobs that are pushed in. Before it begins, it checks the checksum folder to make sure that there isn't already a checksum existing for this file, because there is the potential for it to hit the same file many times if ingest is a bit slow. It launches the make output MD5 function, which in turn launches the MD5 65536 function, which is the amount of bytes that each chunk should feature in the hashlib creation. It uses Python's hashlib library to make the MD5 chunks. Another function writes that checksum into a file and then places it within our local checksum folder. And finally, the file is read by media info, and 6 metadata files are created from the technical metadata of the file as well, using media info, and are saved into a media info folder as .txt, .xml, .json. And you can see they include EBU, PBCore, and a number of others. These are later written into the SID digital media record and kept for long-term storage. So they're written as they are at the moment into the header data of our records, but at some point in the future, with our premise workflows, we hope to integrate the metadata from these into actual fields within our digital media records. Okay, so that's our checksum generation script. The MP4 transcode script, which we're on here. This is the script that converts our files, audiovisual files, into MP4 files, and also any image files that are supplied into auto-ingest transcode paths into smaller JPEG versions of themselves. It checks a number of things, including whether or not the file path is actually one of our Heritage 2022 projects, and it retrieves the input date that the SID digital media record was created. Both of these two pieces of information are used to create the path for the MP4 file so that they can be found later on through our DPI browser. There are checks that the file hasn't already been processed as well, just in case there was a move error that didn't move the file out of the transcode folder as it should have done. And then it looks for what type of file it is. So it looks for that MIME type again, whether it's an audio, video, image, or document. Any audio or document files are immediately moved straight into the completion folder at this point because we can't create proxies for those at the moment. If the file is video, then the following checks are completed. Media info again used to retrieve the display aspect ratio, pixel aspect ratio, height, width, and duration data. The MP4 transcode paths are configured from the input date and file name, as I mentioned. And the metadata is then supplied into the create transcode function. So the function separates out all of the different FFmpeg commands into blocks, as you can see there. It's a very long one, this. And in this second block, you can see there are 13 potentially different filter combinations, video filter combinations, which are lots of different kind of crop options that we have for SD608, NTSC SD, 4x3, PAL, 16x9 PAL, HD, and Ultra HD, and files bigger than UHD as well. Each of these video filters has FFmpeg's black detect within it, you'll see, towards the back end, which captures all the start and stop times throughout the transcode where there are black frames found. And it logs the start and stop times, which the Python later extracts into a dictionary of black frames, so it can be used later on to help select a piece of video for the JPEG thumbnail extraction, avoiding those areas of black where, say, a documentary fades to black, for example. So it looks to pick actual image and not black areas. It also processes a few different video and audio mappings before making a basic aspect ratio calculation at the bottom, which divides the width of the image by the height and rounds that to 3 decimal points, which it uses later on in the command. Then the final section of the FFmpeg command building script runs through a series of potential height and display aspect ratio, or height and width, or height and par options to best match the video information that's being input into it. And from here it populates a variable called command mid. So it's basically selecting which of those 13 video filters are the best match for the file that's been supplied into it. And this is kind of a growing piece of work. Every now and then, particularly from Lucy's digital operations teams, we have another file which doesn't sit within these kind of 13 options, and so it just ends up sitting in the transcode folder for a long time, and I have to take a look at it and see where it's not, where it's falling through the gaps, so to speak, in this plan. And then we keep expanding it as we go. So that then supplies the command back based on whether or not there's audio, and a couple of other things back into the main script. Once the command's returned, a log with the full command is then output. So if it fails, I can go back to that log and see what the FFmpeg command is that was used, and then run it manually myself and see where it may have failed. So we time then the actual Python subprocess call again to make the transcode to MP4. The finished file is checked with the media conch policy against an MP4 policy that we have, and it's looking for a pass or a fail again. And then next, the JPEG image is created from within the actual MP4 transcoded file and not the original source file. The adjust seconds function is launched to attempt a few selections of a point in the MP4 stream, and the FFmpeg logs and captures a red line by line to get that retrieve black space information into the Python code. So when it selects one of many different options of potential second timings there, it checks that black space information to make sure that it doesn't actually land on one of the black frames. Okay. So next, the getJPEG function is launched, which uses the seconds returned from that adjust second to create a JPEG file using FFmpeg. And from this FFmpeg JPEG file, 2 JPEGs are created using open source software Graphic Magic through the command line. This software allows image manipulation of the files, so the JPEG can be resized to a standardized size for our thumbnails and for use in the DPI browser. That's the function there. And then when all the MPEGs and JPEGs are created successfully, the extensions are removed in this little bit of code here, which is a necessity for how we've got our image viewers configured. So finally, any images that make it into the transcode folder are measured into 4 groups. So this is just TIFF files, for example, through our documents teams. If they're between 100 and 200 megabytes, then they're reduced to 75% of their original size for a JPEG proxy image. If it's 200 to 300, it's 60%, and up to 30% of its original size for an over 400 megabit file. Again, this is completed using Graphics Magic command line tool, using the same functions for the resizing for the thumbnails. The JPEG files are checked for their paths and the JPEGs removed again. And then when all of these proxy files have been created, the SID media record is updated from this Python script with the file names of the proxy files that have been created. And that makes them available in the DPI browser for viewing. So that's really all of the new Python scripts for the Imogen replacement. Hope it wasn't too confusing. There's a lot of data there. I appreciate that. What we have next is a really quick look, because we're out of time, just to look at the DPI downloader. So here's a group of, so this is how my Flask DPI downloader looks at the moment while it's still operational. We've got two versions in our repository. One uses the SQLite MySQL database and one uses the Elasticsearch. They're both still available to view in the repository. They both work exactly the same way, except they just look up the information collected from the web app in slightly different ways. The downloader allows users to select a path to download to, a type of download, which is either a single or a bulk download, and also gives a few limited transcode features. So it will transcode to ProRes, to MP4 access copy, or MP4 with a watermark, or it will also create a proxy file for viewing in the DPI browser. The DPI downloader, which is still in final stages of production, has now integrated this, it's removed the need for the Flask app that I created, and it's integrated it into their own DPI browser viewer. But all the Python code is still operating in the same way. It provides us with authentication access, which wasn't easy to implement in the existing tool that we'd built ourselves, because don't have that skill set within our team at the moment. And all of the Python code for the Blackpearl downloader and the ProRes transcoding, MP4 transcoding, is available on the repository as well, so do please take a look. And a final page, just a sincere thanks to these pieces of software that made all of this scripting possible. Python, FFmpeg, GNU Parallel, VLC, Media Info, Media Conch, MKV Toolnix, which I didn't actually get a chance to talk about, but we do manipulate contents of an MKV wrapper with that software in the automation processes. Linux, obviously, Raw Cooked, and Graphic Magics. And also a massive thanks to that team in that photo there. That's no time to wait, I think 6 or 5, many of whom build these things and support us in using them. So thank you very much. Okay. Sorry, I'm a little bit late there.
Questions? Dan, help me out. Sure.
Hello, thank you for the wonderful presentation. A quick question about this Netflix file. Could you share more about its considerations and challenges in ingesting this particular format file?
Sure, I can do my best. I think my colleague Lucy might be better for this one. Was that? No? She's saying no. Okay. Well, there is an automation that I've built, which I can talk about. So in the interoperable media format packages that we're receiving, we're getting MXF wrapped video files separately supplied to MXF wrapped audio files, separately to XML files, which I believe in the XML files we have like a packing list, we have an asset map, and we have a third XML which has all of the information for the full package in there. CPL, thank you. What we're having to do is to automate the way we integrate those into the scripts. So the MXF files, we're not transcoding any kind of proxy images for those. We are making sure that they're all linked on one item record in our digital media database, but they all have their own SID digital media kind of record, so they all link back to the item record, all items in there. So we're having to automate the way we name them so that they all have the part holes for the one IMP package, but they're actually all ingested as separate items into our workflows, if that makes sense. It is the first IMP I think we've had to deal with, so it's been a really interesting learning curve, but we've got the automations in place now, and they're available to view on the repository if you want to know a bit more.
I think we had a remote question, but it was one I missed from the first part of your presentation.
All right. So can you tell us a bit about your comparison process for deciding on the CRF level 28 in your FFE1 to H.264 transcode process?
Yeah, absolutely. It was informed by research where I found a number of people saying that CRF 28 was one of the very highest settings you could have before the compression was actually visually obvious. So we ran a few tests across a few different CRF settings, and 28, on a number of examples that we looked at, didn't actually seem to be any visually different to any of the earlier CRF numbers. And it wasn't a long and detailed process of explanation of research. I think we opted for it because visually we couldn't see any difference, but we knew that we'd be saving a lot of file sizes. And when you've got, say, a few 100,000 files being created as MP4s and stored in a QNAP server, that size difference is quite useful. It's only an access copy for people to view, so they can still access and download the original file if they want more detail and more information from the files.
Not a question, but just to flag that Joanna actually deserves a lot more credit, because Imogen actually went away in March 22, not 21. So just the fact that just the fact that you've implemented all of this, and the decision was quite late in the day to not continue with Imogen. And as you've probably heard, we create a lot of data every day, and we couldn't just let it sit there not ingesting. So the fact that you created all of these applications and scripts in such a short timeline is just phenomenal. So you deserve even more credit. So thank you.
That's very kind of you. Sorry, that mine not getting the date correct is probably indicative of the chaos in some of the workflows that we have going on at the minute. Just to say about the repository, it's kind of a work in progress. As Lucy's pointed out, we've just come out of a very intense kind of script creation period. It's now a little bit quieter, and I'm hoping that in the near future, new tests are going to be implemented for the scripting, because there's no testing infrastructure at the moment, and that there'll be refactoring work going on, and that the intention is to move it into an Airflow workflow. Airflow is like a workflow management system which schedules your processes for you instead of using crontab, but then also provides like a web GUI front end. So from this point forward, hopefully there'll be more tidying up of the code base, but I still feel it's valuable to share it as it exists now, because at the moment it's a better learning tool, I think, for new developers than when we've, say, built it into an Airflow environment. Thank you, Lucy. That's very kind of you.
Any more? It is time for lunch. Okay. And I'll say there's some glassware outside, but it's for the 3 o'clock break. Lunch is on your own. There'll be 2 workshops at 2 o'clock, one for Media Info, Media Conch with Jerome, and then I'll be in here doing a live stream workshop of group projects. In the program, it listed a tour at 4 o'clock, but unfortunately there will be no tour because you've already, walking in here, seen pretty much the entire space. So we'll see you back here at 2 after lunch. Thank you, Joanna, so much.
Pleasure. Thank you.
Hey folks, if any of you guys are here for Jerome Martinez's workshop on media info and media cont, we're just going to meet out here and head over to that workshop space. Otherwise, the live streaming workshop will start in a few minutes.
Unless you want me to stream it.
Projector's on. And I assume that room is packed right now. Hi, everybody. I suggested having this workshop after the live streaming experience at No Time to Wait in The Hague last year, because we arrived, but we were a bit unprepared that year, so it was a lot of like trying to build a live streaming setup as we went. So this table, there's usually a table like this at every No Time to Wait conference, and it's just like how we connect to the outside community. If you look at the registration list for this year's No Time to Wait, it always ends up being a little over half of the participants are remote participants. And one of the volunteer roles we always have at No Time to Wait is that somebody is in the room acting on behalf of the remote registrant. So when it goes to question and answer time or something, like somebody in the room is